Today we're going to talk about the fine structure constant. Now this is a constant that historically physicists like Richard Feynman have laid awake at night and wondered about and pondered about. What is this, this alpha? They use the Greek character alpha to depict this constant. And so today what I'm going to do is I'm going to do a little bit of decoding. I'm going to decode the fine structure constant. Now, why am I doing this when, historically others have done this and maybe it's already done, maybe everyone already knows what alpha is, but that's not how I roll. That's not how I work. And so in order for me to understand alpha, I have to do it myself. I have to find it myself. I'm a seeker. Okay, I am a seeker. I'm not even really a teacher. I'm not a professor. I don't profess things. What I'm doing is I'm trying to figure things out for myself, because when I figure things out for myself, I understand it better. And so really, my video series is my journey. It is not me professing this or professing that, or the ether exists or the ether doesn't exist. I'm trying to figure this out for myself. And so if you want to take this journey with me, then of course you should watch my YouTube video series. But if you think I'm trying to tell you something, or if you think I'm trying to tell you something that you don't already know, or anything like that, then you're mistaken. I'm on a journey, and today the journey is going to be about alpha. It's going to be about the fine structure constant. So this is from the Wikipedia page on the fine structure constant. This is alpha, what I call the many incarnations of alpha. So this evaluates to alpha, and this evaluates to alpha, and this evaluates to alpha, and this, and this, and this, and this. So all of these accumulation of constants evaluate to alpha. And I think this is what makes it so mysterious, because it sort of kind of pops up everywhere. But when I look at this, what I see is computer code. What I see is something that needs to be decoded. And as a computer scientist, when I look at something like this, what I see is spaghetti code. I see really bad code. I see confusion. I see multiple people writing this program and trying to piece it all together. And so this looks like a little bit of a kludge to me. I think this can be very much simplified. And so I'm going to start by simplifying alpha and showing you how I would do it if I were in charge of theoretical physics. So the first thing I do when I'm trying to decode something is I look for patterns. So I look for similarities. And the first thing that stands out to me is that all of these incarnations of alpha contain an E squared elementary charge squared term. Elementary charge, elementary charge, elementary charge, all except for this one. Okay, so elementary charge squared, elementary charge squared. So let's have a closer look. We're going to have a closer look at this one. Okay, so why is there no E squared in this term here? And so this is pretty easy to figure out, because this RK here is another constant of nature. It's called the von Klitzing constant, discovered by a guy named von Klitzing. And what I say is, yay, yet another constant of nature named after a person, named after a man, of course, because I don't think there's any constants of nature named after women, but that's neither here nor there. This is just another constant of nature that we have to memorize. And so I don't like that. I don't actually want any constants of nature that are named after people in my specification. I want only constants of nature named after whatever it is that the constant is about. And so when you map out this here, this little term here, this von Klitzing constant turns out to be h over e squared. So I'm not really sure why this h over e squared needs to be named after anyone, because it's actually just h over e squared. But then you can see that there is an elementary charge squared term in this term here, and it's written like this, and so that is the first part of the decoding, where I put this on the same, terms as all these other ones where they have an e squared term in it. So this is a good clue, the first clue as to the true meaning behind the fine structure constant. So the next thing I want you to notice is that some of these terms are written in terms of h bar, which is reduced Planck's constant, and some of these constants, like the one I just derived, and this one, are written in terms of unreduced Planck's constant, or h. And so, but when you work this out, you will notice when you take this a little bit further, you will notice that, of course, h, Planck's constant, is 2 pi times reduced Planck's constant. And when you combine these terms, you get 4 pi h bar. And then you will see that this one here is actually this one in disguise. So this is in terms of permeability. This is in terms of permeability. These two are actually, the same term. And so what I'm going to do is I'm going to remove that one. So I want to define all of these terms in terms of reduced Planck's constant, just for consistency. Now, the reason I'm using reduced Planck's constant here is because this is from Wikipedia. This is what mainstream does. So mainstream uses h bar quite a bit. And so I actually don't. In my specification, you will notice that I don't use reduced Planck's constant, and I define all my other constants in terms of non-reduced Planck's constant. So quantum of momentum is Planck's constant divided by speed of light, and quantum of mass is Planck's constant divided by the speed of light squared. And so if I wanted to use reduced Planck's constant, I would have to change this and then recalculate this and recalculate this. So we'll talk about that a little bit later. So next we're going to deal with this term here, which also was written in terms of non-reduced Planck's constant. And this term here refers to the impedance of free space. And so let's go over, for the sake of argument, let's go over some of the terms in here just in case you are unfamiliar with them. So this is the permittivity of free space. This is the permeability of free space. This is the Coulomb constant. Okay, we've got the permittivity of free space here again, and we've got the impedance of free space. We also have elementary charge squared, the speed of light, and reduced Planck's constant, and normal Planck's constant. So this is what I'm trying to simplify here. And so this term here can be rewritten like this. Okay, so you've got this term here where we have a non-reduced Planck's constant, which is 2 pi times reduced Planck's constant. And when you multiply this term through, you get elementary charge squared times the impedance of free space times 4 pi h bar, which is this one here. So these two are in fact the same term. They're just written a little differently, and so I can blank out this one. So now that's two terms in this set of terms here that reference alpha, that reference the fine structure constant. There's two that I don't have to worry about because they are here and here. So now we're going to have a look at this one here, which is written in terms of permittivity of free space and is also using non-reduced Planck's constant instead of reduced Planck's constant. And so this maps out like this. So this term here, we do the same treatment to the unreduced Planck's constant, and we get this term here. And when you multiply the 2's here, you get this term here, 1 over 4 pi E0, or sorry, permittivity, which, of course, 1 over 4 pi times permittivity is the Coulomb constant. And so, so here we have this one is actually this one in disguise, and this one is actually this one in disguise. So what we can do here, what we can do now is we can kill this one, we can blank out this one, and we can blank out this one. And now we're left with 3 terms. One is written in terms of the permittivity of free space, one is written in terms of the permeability of free space, and one is written in terms of the impedance of free space. And so I've simplified the code significantly through this process. These are the only 3 we need to be looking at. So before I move on, I want to just talk a little bit about Planck's energy equation. E equals Planck's constant times the frequency of light. Now, and I also want to emphasize this extra 2 pi that is in the equation. Now, when you take, Planck's constant, non-reduced Planck's constant is 2 pi times reduced Planck's constant, or you could say that reduced Planck's constant is Planck's constant divided by 2 pi. And so I just wanted to map out here that there is a 2 pi in this equation, and depending on where you put it, the equation reads differently. And so I pulled out the 2 pi here, and you can see when you group it, when you group the 2 pi with the reduced Planck's constant, you get non-reduced Planck's constant. But if you group it with the frequency term, when you group it with the frequency term, then you have to use angular momentum. Okay, you have to use angular momentum. So in physics, generally, if you use h bar and you don't see a 2 pi in the equation anywhere, you can assume that they're talking about angular frequency. And so 2 pi or not 2 pi, that is the question. Do we use angular frequency or do we use regular frequency? Well, in oscillation mechanics, I don't use angular frequency, at least not at this point. I'm not using angular frequency, and because I'm not using angular frequency, I have to use non-reduced Planck's constant. So I wanted to go over that a bit. I also want to read you this little section from the Wikipedia page on Planck's constant. Actually, ironically or coincidentally, one of my viewers sent me this yesterday. His name is Dragon. I hope I'm saying that right. Thank you for sending me this, because this is an important point that needs to be made. I'm just going to read this to you, okay? So, confusion can arise when dealing with frequency or the Planck constant because the units of angular measure, cycle or radians, are omitted from the SI standard. And so in this little paragraph here, they're admitting that they omitted the cycle term, which I'm trying to put back into modified unit analysis. So in the language of quantity calculus, the expression for the value of Planck's constant or a frequency is the product of a numerical value and a unit of measurement. The symbol F for frequency, or mu, or nu, sometimes they use nu, when used for a value of a frequency implies cycles per second. Okay, so they took cycle out and now it's just implied. So when the symbol omega is used for the frequency value, it implies radians per second as the unit. So if you use angular momentum, now you have radians per second. And that's why I don't use omega, because I am doing everything in terms of cycles. Okay, so this is just the way that I'm approaching everything. And so the numerical value of these two ways of expressing the frequency have a ratio of 2 pi, which I am showing you right here. Okay, they have a ratio of 2 pi. So omitting the units of angular measure, cycle, or radians, okay, can lead to an error of 2 pi. So if you do it wrong, if you use h bar in an equation, okay, if you use h bar in an equation, but you use frequency instead of angular frequency, you're going to make a mistake. Okay, so so where was I here? The symbol h is used to express the value of Planck's constant, and the standard way is joules times second per cycle. Okay, so they're admitting here that in mainstream, the Planck's constant is joule times second per cycle. Second per cycle is the units of the period. Okay, seconds per cycle is the unit of the period. And so the units of Planck's constant, at least the way I read this, is joules, the energy of one period of time. The one period of time is the length of time of one oscillation of light. So mainstream reads this as an action constant, but when you put the term cycle in here, this reads as energy of one period. Okay, energy of one period of light. And so this is the point I wanted to make here. I know that mainstream reads this a little differently as an action constant, and they ignore the cycle term, but when you put the cycle term in, it's very clear that the Planck's constant is the energy of one cycle of one oscillation, one wavelength of light. And so this is at least how I read this, and I think that I'm justified in doing it this way. So I just wanted to bring that up, that they're admitting that they're omitting the cycle term in the standard, and in modified unit analysis, I'm just putting it back in where it belongs. So thank you, Dragon, for sending me this yesterday. It is a really nice addition to the video that I've been working on for the last week or so. So this is really nice. Thank you. So here you can see the simplified code for alpha for the fine structure constant. This term here is written in terms of the permittivity of free space. This term here is written in terms of the permeability of free space. And this term here is written in terms of the impedance of free space. And so the numerical value of the fine structure constant is this, which is approximately equal to 1/137. And so now, next what I want to do is I want to see what happens when I replace h bar here, reduce Planck's constant, with Planck's constant. So I'm actually going to calculate alpha, calculate this value by replacing reduce Planck's constant with with Planck's constant, because I want to see, because in oscillation mechanics I use non-reduced Planck's constant, and so I'm going to get a different value here, and so the value that I'm going to use is going to be different than the value you use when you calculate these three terms using reduced Planck's constant. So that's what I'm going to do next. So here are these three terms written in terms of reduced Planck's constant, and now I'm going to write them in terms of non-reduced Planck's constant, and I'm going to give this constant a different name, a different label, because this is going to have a different output. And so all I did here was I replaced h bar by h, and I left everything else the same, because this 4 pi belongs to, in this term here, belongs to permittivity, and this 4 pi belongs to permeability, and this 4 pi belongs to the impedance of free space. And so when you do this calculation, you get this value here, and this value here is the anomalous magnetic moment. Okay, this is the anomalous magnetic moment, and of course I've written it to as many decimal places as my computer spits out, but really, so this is identical to the anomalous magnetic moment, which is alpha divided by 2 pi. So let's go back to here. So you can see there in Planck's energy equation, there is a hidden 2 pi, and when you assign 2 pi to the to Planck's constant, so 2 pi times reduced Planck's constant is standard non-reduced Planck's constant. So when let's look at it this way: when Planck's constant has the 2 pi, when Planck's constant has the 2 pi, then you have to reduce alpha by 2 pi. Okay, so since in my specification I use Planck's constant, I can't use alpha. I have to use this term here, which just happens to be the anomalous magnetic moment. The one loop contribution to the anomalous magnetic moment corresponding to the first and largest quantum mechanical correction, oh boy, of the electron is found to be blah, blah, blah. So, you know, they have their idea of what this is, but I'm not going to make any assumptions about what this is. All I know is that when I am calibrated to Planck's constant, I have to use alpha divided by 2 pi, because my Planck's constant already has, not my Planck's constant, but the Planck's constant that I'm using already has the 2 pi, and there's only one 2 pi in the system. And so 2 pi or not 2 pi, when I use Planck's constant, I think of Planck's constant, think of 2 pi as a hot potato. Okay, it's a hot potato. Planck's constant, when I use non-reduced Planck's constant, it's got the hot potato, and so I have to reduce alpha by that hot potato. And so the anomalous magnetic moment and alpha are actually one and the same thing. When you use Planck's constant, non-reduced, you have to use the anomalous magnetic moment. And when you use reduced Planck's constant, to calculate alpha, you're going to get the standard alpha. And so all of these terms using non-reduced Planck's constant and as opposed to reduced Planck's constant, they all evaluate to the anomalous magnetic moment. So for me, this was a huge piece of the puzzle. The anomalous magnetic moment isn't something different than alpha. They are one and the same thing. It really depends on how you calibrate your system. And so calibration is, my understanding of calibration has really helped me to sort through and to decode alpha, and to the realization that the anomalous magnetic moment is exactly alpha. And, it might interpret differently because I'm using frequency and not angular frequency. When you use angular frequency, you have to use standard alpha. But I don't really, I don't want to use angular frequency for the reason outlined in this Wikipedia page, because I don't want to use radians per second. Radians per second isn't as meaningful to me as cycles per second. And so if I want to use the terminology of cycles per second, I have to use Planck's constant. And when I use Planck's constant, I have to use the anomalous magnetic moment whenever alpha appears in an equation. And so that really clears things up quite a bit for me. At least, it really helped me think this through. But we still don't really know what alpha is. And so I'm going to take this one step further. I don't think I'm going to be able to put this all into one video, but I'm going to give you a clue for the next video as to what I believe this means. So let's go back to the original Wikipedia description of alpha, just to remind us about of how much we've been able to simplify this code. Okay. There are many ways that you can express alpha. That's the point of this, I think, that there are many ways that alpha can be expressed. But wait, there's more. There's one more on this list. It's not on this list. There's one more that I found that's not on this list, and that is this one here. And so this is elementary charge squared divided by Planck charge squared. Okay, and so what is Planck charge? Okay, what is Planck charge? So Planck charge is calculated using the permittivity and permeability of free space. And so Planck charge is actually a constant of nature. And so this constant of nature is calculated using the other constants of nature. And so it's also equal to elementary charge divided by the square root of alpha. And so, but what is Planck's charge? This is actually more of a quest for me than what is alpha, as you will see. Okay, so what is Planck's charge? But more importantly, where is Planck's charge? Okay, so let's go back to this. Okay, alpha is equal to elementary charge divided by Planck charge. And as I showed you earlier, elementary charge is in all of these terms, and it's hidden in this term as well. And so where is Planck's charge? Like, where's Waldo? Where is Planck's charge? Or more importantly, where is Planck's charge squared? Because here we have elementary charge squared, and so here is where Planck charge squared shows up in all of these alpha terms. So this is Planck charge squared, and this is Planck's charge squared, and this is Planck charge squared, etc., etc., etc. So the other thing I want to point out is the standard way of calculating Planck charge. If you go to the the Planck units, the Planck natural units, Wikipedia page, you're going to find that they calculate Planck charge using reduced Planck's constant. And so I don't do that. I actually use normal Planck's constant because of the way that I'm specifying everything. So since I am using Planck constant and not reduced Planck's constant, when I calculate Planck charge, I have to plug in the non-reduced Planck's constant into these equations. And so so this is where Planck charge squared lives in all of these terms, So I want to know what that is. Okay. My quest now is not to understand alpha, because I think I understand alpha. Alpha is just it is unitless, it is a scaling factor, it is a reduction factor, depending on how you look at it. And so, and of course, I don't use alpha. I calculate Planck charge using non-reduced Planck's constant, and because I do that, I have to use the anomalous magnetic moment. Okay, I have to use that term, that in my equation. So that is, I'm going to leave that. I'm going to leave that for the next video. What is Planck's charge? I'm going to try to answer that in the next video. Understanding alpha, the fine structure constant, has led me to here. It's led me here. And so this is where the next video is going to start. It's going to start with Planck's charge and what is this relationship here. This relationship here, which is alpha, which is also the anomalous magnetic moment when I use Planck's constant and not reduce Planck's constant. This relationship here needs to be understood. And so that is where I will pick it up in the next video. So thank you very much, and well, I guess I'll be back.